It's an honor to welcome Jörg Dörstein from BioFiber back on stage. When the Innovation Awards were presented for the first time 5 years ago, his team and him were the winners of the coveted trophies.
Yeah.
After completing his Master of Science in Renewable Resources at the Technical University of Munich, he was a doctoral student at the Chair of Biogenic Polymers at the Technical University of Munich until 2016. From 2017 to 2021, he was Head of Research and Development at BioFibers GmbH, where he was being Managing Director since 2022. Today, he will present about the steps done to offer bio-based binder systems. A warm welcome to the Managing Director, Jörg Dörstein from BioFiber, with his lecture on the topic Bio-to-Compound Continuous Processing of Microscale Functional Fibers into Bio-based Binder Systems.
As you can see from our brand name, or let's say company name, BioFiber, we have been heavily dealing with natural fibers, with biofibers, in constellation, in compositions with conventional plastics in the past, and nowadays with the main focus on biopolymers and bioplastics. So. Just a few words about BioFiber. From our background, we are an offspring of a machinery producer. The LWB Steinl is producing injection molding machines for the plastics industry, and we have recently opened a production facility in France, so pretty much already an European company. And back in 2022, we opened a sales office in Sao Paulo, Brazil. But nowadays we are a joint venture due to our shareholder constellation, where we have access to pretty much a lot of locations throughout the world, with the main focus on Middle Europe for sure. But whenever there is potential in terms of feedstocks and as well for markets, we can easily reach out wherever cars are produced, more or less. We can have easy access on it. A black spot in Australia, so has to be fulfilled. So BioFiber, what's that in general? To give you a brief overview for those who are not familiar too, I expect that most of you know about natural fiber reinforced plastics. By combining renewable fibers, as we heard before, the best is to use leftovers of different industries like agricultural industry, forestry industry, or fishery industry, and we combine them with bio-based additives that are renewable, compostable, and free of toxic substances, and yield a granulate material that is thermoplastic. In best case, when you use natural polymers, or we combine them with other bioplastics that are renewable, lower in carbon footprint, and have high performance depending on the application. So back 4 years ago, we were frequently asked for applications that require thin-walled injection molding, for example. And then we came to a level where we could not go below, for example, 500 micro or 0.5 millimeter in wall thickness. And another aspect was that the fibers that are bigger in size, or macro scale, they are blatantly visible, and for example, for film application, this is not desired. Clients desires, for example, translucent products. So we access the market of microfibrillated cellulose, and to see how to combine those micro-scale fibers into bioplastic binder systems, but as well other binder systems, natural binder systems. So for those of you who are familiar to MFC, or microfibrillated cellulose, I'm certainly not talking about secret, that they are quite hard to be handled. They are most of the time in the presence of water, like suspensions. You can go up to 30% of solid content in those suspensions that are dosable and pumpable. But if you are using this in a conventional extrusion system, you pretty much and very fastly see something like a steam engine, and you generate a lot of moisture and a lot of gas and vapor. So the idea and let's say the concept was that we involve our machinery team from the LWB Steindl, our mother company. We are developing a new continuous process for the gentle incorporation of MFC. In particular, what we saw before, we talk about polyesters that are hydrolyzable easily in contact with water, so we need a specialized and really gentle process. But in the end, it has to be efficient and price competitive in the end, till the point of the product stage. So what we saw is the potential of natural fibers, and in particular nanoscale to macroscale fibers, that they can impart strength and stiffness. This was our initial idea. And then we can have as well some nice aspects and benefits in terms of barrier properties. What is as well challenging for many bioplastics we heard before is when we talk about compostability. Most of the time certificates are restricted to some microns, like some 50 to 100 microns film applications. But when we talk about injection molding parts, you talk about at least those 500 microns up to 1.5 millimeter for some packaging applications. So talking about nanofibers, as this is envisioned to be one solution for those issues, we looked into what we have already in stock, and we saw that natural fibers can be divided into being a reinforcement to bioplastics or just a filler. It's largely dependent on the aspect ratio. This means that the length to diameter ratio has to meet a certain level, and then you can talk about the strength imparting and stiffness enhancing reinforcement, let's say, and you can uptake forces during the application. And in contrast to that, you talk about a filler-like behavior when you talk about the length to diameter ratio to 10%. This is let's say an empirical equation, and it's a definition in how to divide those two geometries. And what we saw is that when you combine those two different geometries, you can enhance the mechanical properties in terms of brittleness or toughness over the E modulus. And when you just use natural fibers into composites, and you can have some certain enhancement of the E modulus, but still you have to cope with brittleness in the composites. But if you hybridize this, and if you have to fine-tune the different geometries, you can drastically enhance this ratios, and it gets tougher and stiffer through this balanced hybridization. But why is compounding, in our view, one of main thing which can enhance our bioeconomy in terms of bioplastic? You have the ability to tune properties of biopolymeric systems, like for example mechanics, optics, biodegradation, and you can be much more cost efficient and be flexible. When you talk about big polymerization units, for example, that need to change their aim or target polymer quite often, then you have losses in efficiency, and compounders can meet the same goal. Like, for example, a defined mechanical property can be easily tuned, or let's say a much more price competitively tuned than a big polymerization unit. What we saw before as well is you can tune some functionalities, and I want to shed light on the barrier properties, what we are coping with here, and it can really support the biopolymer business, and not to have too many niche grades in the portfolio. But when you come down to the nanoscale fibers, some of you know already that those nanoscale fibers are largely shear thinning. It means that it behaves like a solid if it's in rest or you don't move it. But once you are moving it through screws, through different mechanical forces, then you can really make it into a stage that it's behaving like a liquid, and it gets even more prevailing if you enhance the solid content. So pretty much the stage of 1% solid content is something like you can compare with oil, or let's say something like a jelly material. But if you talk about 10% MFC, you really already talk about let's say at least a chewing gum, and when you go up to 30% MFC, you don't believe that this can be flowable just by sharing forces. Just one illustration of this. This is 10% of MSC, so 90% of water behaves really, really sturdy, let's say, and needs to be introduced into the compounding device. This was the challenge. So what was the aim of this project? The aim was to have an efficient material that can really compete with PE, PET, PET in many applications, not only from a cost perspective, but as well from the performances, to select the key properties and meet them with the new technology. We talk about an ecological approach, that we are not making compromises on being bio-based or biodegradable. Ideally, we talk about both, and depending on the binder system, we can meet both goals. And it should be economically efficient, so no solution processes. So this has to be met, or we envision this to be met during a compounding process. So once to meet the material properties, you have to talk about as well the biodegradation, you have to talk about the bioeconomy, and then there is a trade-off between the process and the recipe formulation, and this is where our partners come into play, our university partner, which I mentioned later on, and the aim is to have a performant bio-based and biodegradable material system for the sake of getting reinforced material that is lightweight, can be biodegradable, and can enhance the biodegradability through the incorporation of readily biodegradable compartments that are, let's say, prone to uptake water and release surface area for the biodegradation, and to have a functional material that you cannot really see that there is a fiber inside incorporated, but has functionality inside, and have barrier properties that overcome other mineralic fillers, for example. And then you have a processability that you can make sure that you can process those materials. What we achieved last year was a continuous water-based and fine dust-free compounding process with a drastically reduced amount of water, which is one of the key aspects. And we tried this with PLA-based materials, but as well with PHA based materials and PBS based materials, and it works quite well, and we have an even and fine distribution with really interesting properties. And these basic tests successfully were completed, and the functionality was proven in 2023. What we saw as well is that once you introduce just the nanocellulose or the microfibrillated cellulose into the binder systems, you have something like voids between fibers and matrix. So one of our main goals was to compatibilize in the right way. So sometimes you need the voids, sometimes you don't need the voids, depending on mechanical requirements, depending on biodegradation. So there is no bad material, there is other materials. That's why we pretty much tuned around between being really hardly bound to the matrix, and to have compatibilization that is really making the fibers adhere to the matrix material, as since the polarities are in many cases quite different. What we saw as well is that once we introduce those nanoscale fibers, they have dimensions in the nanoscale, in the microscale. They are as well working as seeds for crystallization. You can drastically enhance the crystallinity, as well the cycle time and injection molding process. And to our astonishment, we could reduce the melting area to lower values, which can help as well for various applications like different self-fiber reinforced applications where you talk about crystalline materials and amorphous materials, which can really be beneficial. We saw as well that you can have the degradation control through to the reduction of the melting point, which is more or less as well empirically at least related to the intermolecular forces between the chains, which means as well that the accessibility of those polymeric chains are better for microorganisms, and you have some barrier properties enhanced in terms of, in particular, oxygen. So we tested quite a lot of different compatibilizers. Some worked quite well, some didn't work very good. So it was just an easy drop test, and it was our first approach to this. But testing it in a compounding unit revealed that just by exchanging the compatibilizer, you can drastically change the material properties. For example, you can have the tensile strength in a ratio between 20 to 20% plus to 20% minus. Or most strikingly was the E modulus, where you can enhance the E modulus because of the embedment of the fibers into the matrix, which was much more elaborated when you use the compatibilizer. And if the compatibilizers bears, for example, nutrients, like we heard before, N-bearing nutrients, you can control as well the biodegradation. This helps us to looking to our customers' demand, which approach us with from different sectors and different point of views. Here is depicted the product life distribution of different segments over the endurance time or the application time. And we see that there are applications which just rest for some minutes to some years, like packaging, and others that are more related to building and construction. In our point of view, the nanoscale fibers can have a really good benefit in those applications where you can talk about some years, like, for example, packaging, consumer goods, and textiles. Whereas in cardboard storage solutions, we see as well some potentials, but quite restricted right now, but we see some potentials in how to combine them with other fiber systems. the aim of all of those materials should be as well, despite the fact that they are biodegradable or can be biodegradable, that we have as well an atmospheric carbon embodiment in products, which is really a big means to reduce the atmospheric carbon. So to put the whole thing into a nutshell, the microscale fibers can enhance biopolymers. We showed that we can have a continuous compounding line that is ready for tests, and we can join forces if you have new ideas. We can work on customer-specific requirements quite easily, since we have done some homework on fine-tuning recipe formulations, processing devices, and we can tune properties within the compounding line, compounding step. What we saw is that it's right now not that easy to have a really certified and sustainable nanoscale fibers. So for those of you who come from the feedstock side, there are some challenges to be done and certifications to be done on this point of view, since there is a lot of energy involved, but there are new concepts, and it's quite promising to get the carbon emissions down during production of those systems. And what I can just communicate is that choosing the right fiber morphology and the constellation between different geometries can really drastically tune the properties. The compatibilization with compatibilizers is even enhancing this property tuning. So I'm very happy to talk to you in the breaks and now in the Q&A session, and thank you very much for the attention.
Yeah, thank you, Jörg. Quite interesting topic. I think modifying biopolymers to fine-tune is one of the main topics of the event today. So happy to welcome you as audience to pose questions, as well as online. Feel free to come over here to the microphone if you're here present, or put them in the chat.
Do you provide that also as a master batch in a higher concentration, that we can use it in our compounds easily?
Good, very good question, and indeed this was one of the aims of this publicly funded project. At this stage I need to thank the Technical University of Munich and the Public Funding Board as well. I missed that out. For sure, we went up to a system that bears 30% of MFC within a composite, which means as well, what we saw is sometimes for some application, like for example gas permeation, you just need 2% of MFC in the compounds, which means that you just use 5%, for example, of this master batch, and then you can have the right fit.
Quick question from the audience from online. Do you can also produce with your compounds textiles? Right now not, to be frank, and we are working on systems that show motifs that are below 20 micron, for example. Fibers that are lower than 20 micron in each direction. And in this case, we can talk about fiber applications, but it's more filament and really sturdy fibers. We are not yet there for applications like melt blowing, where you talk about 2 to 3, 4 microns. So this is just the current stage. Okay, thank you.
How is the impact on coloring? Is it getting more whitish since the MFC looks white? Is there any shift in colors? Can you comment on that?
What we saw is that when we evenly and fine distribute those fibers in the binder system, then we talk about the translucent material that is hardly being
the fibers are hardly visible, more or less. So you can pretty much color it in every color. There is probably an off when we talk about 10 to 20% MFC, but most of the application which we see is restricted to 1 to 5% of MFC incorporated into the binder system.
Okay. Yeah, we have another volunteer asking a question here.
Thank you. Just another quick question. You showed some results with PLA and PHA that you added your fibers, and you said you got good results. Can you comment maybe on the property improvements? Did you in tensile strength or elongation of break or toughness?
Yes. What we expected is a drastically enhanced mechanical property in terms of stiffness and strength. What we encountered is more or less an increase of up to 30%, which is below our expectations, but still much higher than, for example, PE, which is intrinsically from the PLA already better, but we expected more. What we found out is pretty much that the functionality is the key. It's not about mechanical properties. For us, what we see when we compare to customer requirements, we see functionality like, for example, permeation behavior of different gases like biodegradation, crystallinity, fast cycle time. Those are for us the key aspects in this application, more or less. Less the mechanical properties, at least for what we saw and found.
Yeah, that makes sense. Thank you.
Okay.
Yeah.
Yeah, two questions from my side still. So when are you planning to commercialize? That's more or less in the direction of Peter, maybe. That's his last question. Are there any plans to bring it up to the market soon?
For sure, what we are doing here as well is searching for partners, strategic partners, and we want to commercialize. We want to ramp up as well our technology, and the machinery side is ready, and we are in the middle of providing the next steps. We recently finished the publicly funded stage, but now it should go into the market, and we want to go as fast as possible with MVPs out there.
Very good. And last question from my side, are there any samples available? You talked about injection molding, thermoforming. I mean, you started with thermoforming, which is a kind of interesting two-step process in plastics processing. Any steps done there yet, or when can interested people of the audience can expect some results?
It's pretty much handwork right now, but we are open to provide samples, for sure. This is what we can do with our ready continuous process,
Very interesting. Thank you, Jörg, for that lecture. And we're going to continue.